My name is Jöran Vinzenz. I'm from Germany. I work at a company called Zipgate. Zipgate is a voice over IP carrier and service provider in Germany and in the UK. And we offer both for residential and business customers. We are on the market now for 15 years, 16 years, something like that. And we started our business using Asterisk and kamailio. And since then, we grew a bit. And during the time, we changed a bit, but there was no revolution. So we had to think about a new kind of way to do this telco stuff. And so we came up with the idea to use Stasis app for that. For the schedule for the next 45 minutes, I will talk about the motivation, why we did that, the idea we had what is behind that, how we implemented that. I give a short, brief look on the performance of that all, and then we had some stuff with open source. I will present that as well. So first, the motivation part. For that, it's important, it's more easy to understand. If you know the current setup, I've been to AstricCon 4 years ago and explaining how the setup of Zipgate looks like. And this was the overall picture, how this looked like back 4 years ago. And it hasn't changed since then. So we still have a couple of kamailios, we have a couple of asterisks. So far, there are about 120 instances of Asterisk running. But it's a little bit too big, the picture to show, so we now just looking on this one. So we have the kamailio, we have the Asterisks, and some scripts behind. We have at all 2 bunches of Asterisk, one connected to a lot of AGI scripts running on the local machine, and the other one is connected to fast AGI and AMI services. So we have these 2 different roles of Asterisk service. The first one does basically billing and announcement. This is, I would say, the oldest part of Zipgate we have. So the first part we did was passing calls through, make billing, charge money, and if the money is out, we have to announce, please refund your account, and then you can call again, something like that. And that's pretty much what it does today. And then we came up with this PBX functionality in 2008 for a business product. And we have built up this one, and we put on an AGI, fast AGI script on that running locally on the machine. And we had this AMI connection to a service in the back end, and we grew up, and then we had the problem with scaling. So we just doubled the setup, and now we got this sharding over customer's ID to a certain cluster, would make deployment pretty complicated. So we have to shift all customers to another cluster, something like that. It's a pain. And due to the grown or evolved setup we have, if you're in a certain call scenario, you hit up to 4 Asterisk in a row. So you can imagine what that means to call setup delay and speech delay and so on. Then we have a lot of small Perl AGI scripts we trigger during a call. And for any certain circumstance, we have one Perl AGI script we trigger. And I think we have something about 20 or 30 small scripts we trigger during a call. So this is not very good. For the PBX part, we have a fast AGI monolith, I would say, and practically no one in our company want to touch it anymore because it's so big, and if you touch this place, anything else on the totally other side crashes, something like that. So everything we learned in the software development a couple of years ago, that we don't have to have a monolith, that we can have small scripts or small services, microservices, which does a small thing we want to do. This is what we want to do in Asterisk as well. And then maybe the most important part is we have a highly patched Asterisk 11. And we didn't listen to Matt last year where he told us to update. And we listened not to him this year where he said update, because we cannot update. This is the problem if you have a patched Asterisk. So we want to get rid of that too. And then for sure we have this problem. We use chanzip-c and not pjzip and so on. So it's difficult to just make a drop-in replacement with an actual Asterisk. So we have several demands we have from a telco core team perspective and for company perspective. The first one is, I think it's clear, we have a demand on high availability. Then it should be performant. And if it's not performant enough, we want to scale. So this is what we have so far at the moment with the current setup. So just for that needs, we didn't have to update. But then if it comes to continuous deployment, we have a problem because in the PBX part, as I said, we have these clusters with customers ID sharded on the different clusters. We have a problem when we want to make a deployment on the certain system. So we have to reroute every customer to another system, and then we can update it. And as you know, updating an Asterisk is not that easy. You have to wait for a call to end, and then you can restart it or reload it or whatever. That is a bit difficult. And then we have, I would say nearly all code we have in Perl is untested. So our need is to have not any untested code in the telco system, which is common in software development, but it's not common in telco development, I would say. Then the next one is a little bit more challenging. We want to have a low barrier for entry. So if a new colleague comes in the company, we want to have a big barrier to enable him to develop a new telco feature, whatever. So it's so far he has to learn Perl, and he has to know kamailio config, he has to know Asterisk extensions conf, he has to know the entire setup, and this makes things pretty difficult. And resilience is a demand. So we want to have a kind of self-healing system, and if something crashes, it should continue the service for the customer. Even though maybe some calls get crashed, the overall system should not be influenced of a single crash. So we sat there with all these demands we have and the current setup we have, and we made a decision, which is a bit painful. We will rewrite our entire telco stuff. So we throw away all the other stuff, or we just let them die. And we will do that with Asterisk 15. So it was last year. We will update to 16 now with ARI. Because ARI gives us the flexibility we need. So far we have AGI and AMI, which gives us the control about the entire call. We get the same with ARI, but just one interface. It's pretty easy. So in theory. So we need to change a bit, and today we have these AGI, AMI stuff. We want to get rid of that. We want to have ARI, just one interface for the entire call life. We have this evolved monolith no one want to touch. We have decided that we want to have a modular system where you can just rewrite a small kind of software or a small part of the software without crashing the entire system. And at the moment, these complex call routing, as I said, we have in a certain scenario, you can hit up to 4 asterisks. In the future, we want to have just a single asterisk in a call flow. So this would eliminate debugging time for customer support, debugging time for me. We don't have a multiple jitter buffer. We don't have multiple session IDs whatsoever. So the idea we had, or we came up with, we have kamailio. We use a dispatcher module to basically dispatch calls. At the moment, we use a proprietary system using enum for that. This is just for us, and it's very old, and we still use it. But there is a module in kamailio doing exactly what we need, so we will use it. And even though an asterisk get crashed or something is not right there, you can reroute the call to an asterisk, which is already there or still there. So we have this kind of resilience we need. On the Asterisk itself, we have the Stasis app we start. So with ARI, we get all we need. The Asterisk does the zip handling, the media handling, and we will have a little script on there making all the carrier handling we need. So certain carrier needs certain zip specialties, I would say. So this is something we have to do in the Asterisk. And the entire call logic, so implementing from call hold, call transfer, forwarding, IVR, whatsoever, we will do in a new component called callcontroller. So we will do that, or we have done that, which gives us the flexibility to separate the call logic from the asterisk. So we can, for example, restart the call logic without restarting the asterisk. So this would make deployment much more easy. And as we have the asterisk as dumb as possible, so less config we have in the asterisk, the less we need to restart them. So how does it work? This topic lasts a little longer than the other one. In essence, we have this kamailio sending zip to an asterisk. This is nothing new. Then we have the asterisk, where we have an ARI proxy connected to the Stasis app. So it gets event to the web socket and sending commands to the REST interface. And everything behind the asterisk is pretty new for us, at least. So we use an ARI proxy written by ourselves, and we use Kafka as a message bus, or in this case, more or less a message broker. And at the end, we have a call controller controlling the call. So this is the high-level picture. To drill a little bit deeper, in kamailio, we have the dispatcher module. This is the code from dispatcher module pretty much out of the documentation of kamailio. We will do that at the end using AppLua or Kemi. So we don't want to have untested code, and kamailio config is untested code. So we don't want to have to use it. But there is a possibility to have this in Lua or JavaScript or whatever, so you can test it. But in essence, this will happen in there. Then we have the best extensions conf ever, because that's all. And this is so little extensions conf, we accepted to not have to test it. So it's pretty easy. And then for the ARI proxy and the Kafka, it's a bit more complex. So we get out the messages out of the asterisk using the WebSocket. And the ARI proxy adds some informations like an asterisk ID and a routing key, and put that everything together in a so-called ARI envelope. So this is a word from us, and pushes that to Kafka. So the Kafka has some routing information and the raw JSON object out of the asterisk. The routing over the Kafka is a bit complex. At the first time, we split up between events and responses, so the direction from asterisk to the call controller and the other way around, from call controller with the commands to the ARI proxy. For example, if we have a Stasis start or a channel changed state event, something like that, coming out of the ARI, out of the web socket, we push that on an events and responses command, events and responses topic in the Kafka. And the call controller on the other side consumes this topic and gets the event out of the asterisk. And then the call controller maybe wants to answer the call or send the channel in a ringing state or whatever, or wants to hang up a call, playback, whatever you want to do with that call. It sends out the command through the commands topic through the Kafka. And the ARI proxy on its side consumes out of this commands topic, and then using the REST interface for the asterisk to get this command published on the asterisk side, and the response itself, so we get, for example, for every command we get a response, hopefully. The response is getting on the events and responses topic again. So if we have two ARI proxy running on one asterisk connected to two Stasis apps, then our dial plan would like one line more, something like that. We have commands and responses topics for each and every ARI proxy on an asterisk. So in this case, we have two ARI proxies for maybe different kinds of customers or different kind of called numbers, however you want to split them up. The ARI proxy always talks to a certain events response topic, and the call controller sends the command to a certain commands topic. And the ARI proxy and the commands topic is a one-to-one dependency. So we have for each ARI proxy and each command topic just one connection. So if we have two asterisks with one ARI proxy, as I said, we have this one events and responses topic where both applications, so both ARI proxies sending to the same topic, but the ARI proxy consumes from different commands topics. So the commands topic is specific for an asterisk. This is important that we don't send an answer to a channel to a wrong asterisk server. That would be bad. But to have this, we have this one-to-one dependencies on that. Then you can put that up in a more complex way. We have two asterisks with two ARI proxies, so we have two events and responses topics for the different kinds of ARI proxy, and then we have two asterisks command topics to get back the commands from the call controller. This doubled because we have two ARI proxy for each asterisk, so we have in sum we have 4 commands topics and 2 events and responses topics. So I hope you get it. And then we have the possibility to have multiple call controllers on the call controller side. There we get something for free from Kafka. Kafka does message routing. It's not like RabbitMQ where we have, you can consume out of the message queue and then it's done. So you can address a message while putting it into the Kafka to a certain consumer lag. And the consumer is sharded by the Kafka itself. So it's not sure which call controller you hit, but you hit always the same with the same routing key. So the Kafka routes all messages with the same routing key to the same call controller. So we have this Kafka routing we have to care about because we don't want to have all Stasis start events on one call controller and all channel state change down events on the other one. We want to have all on one call controller. So all events should go to the same call controller and the replies should go to the sender, so to the correct sender, hopefully. So in this case, we check the Stasis start, which is the first event we get on a basic call. And on a Stasis start, we generate a routing key in the ARI proxy. And we save that routing key in a database which is connected to the channel ID. We get that out of the ARI message. And then we publish the Stasis start event to the Kafka. If we have now a channel state change event, which is the second event we get on a call, we have the channel ID in the channel state changed event. So we get out the channel ID out of the event, have a lookup in the database, and get the routing key. Put the routing key on the message and send it out to the Kafka. So the channel state change will hit the same call controller like the Stasis start. Now we have something like a playback events or bridge events or whatever, which are not linked directly to a channel in the first place. But there is, for example, a channel playback command to start a playback on a channel. In this command, we have both the channel ID and the playback ID. So we take the channel ID and get the routing key and take the playback ID and save the playback ID with the routing key in the database. So on the upcoming playback started event, we will get the routing key with the playback ID we have. So basically, it's everything to get everything in the right place. So hopefully, we will never have to touch that again, hopefully. We have one routing key for the entire call. We call it call context because it's not a call. It might be a playback or a bridge or something else. So it's a call context. All commands generating a new resource in the asterisk, like a playback or a bridge or something like that, will update this key map. The only difference is on the Stasis start. This is the only message will generate a routing key in the Kafka. So this is the first message we get. So this is the first key we need to have. We still have, because we are pretty much at the beginning, we still have to do, if, like, for example, a feature like click to dial, where you have a call out of nothing. We have to generate a routing key maybe before we have even a Stasis start. So we haven't figured out that. Then we have the call controller. The call controller have some goals we want to achieve with that. In the first place, we want to have a transparent Asterisk server farm. So as a developer perspective, I don't want to care about how many Asterisks there are. So I just have one Kafka to connect to. And if there are just one Asterisk or several hundreds of Asterisks, I don't care. So I get the Asterisk ID in my ARI event, and I want to address this Asterisk ID back on my commands, but I don't want to care if it really hits the correct Asterisk, so I don't want to do that. Then we want to be as close as possible to the ARI documentation. The ARI documentation is pretty good. I don't know how many of you have had a look in there. So quite a few. But as long as we stick to the ARI documentation for everything we do, a developer can just look up what do I need for this command, or how do I have to form my JSON body, whatever. Then we want to have a restart safe environment. We get this for free from the framework we use, and we want to have an easy to scale environment. So if we see we haven't had, or we have overdone it in the last time and the server have too much load, so we can just add another one in order to scale. For the call controller we did so far, we use a framework called akka. Akka is a JVM-based framework written in Scala. We have written so far all code we did in Java, because we know Java. Akka uses an actor system to address each component internally. So we have kind of domains inside our code. So if we want to change something, we can change just the single actor in order to replace something. And we just have to test the behavior of an actor and not have to test the entire code, because an actor itself has kind of an API. You address stuff to there and it behaves in a certain way. And what it's done internally, you don't care about that. And for the call controller to have something like similar adaptation to the Asterisk, we use a finite state machine, as it's term from the akka's context, which is state machine. So we have a state machine which has a backup in a Redis cache, so even though it's crashing or we restart the system and a new message to a certain call comes in to a system which is brand new, started up, the system goes to the Redis and restores the state machine in the last known state. So we get this for free in terms of restart safe, for free. In essence, the call controller consumes out of the Kafka and sends the commands to the call controller, to the commands topic. And in the call controller, we have kind of a message router to route the message to a certain kind of app or to the specific app for this call. And this is done by a message router. It's pretty simple. It's just routing messages and commands in both directions. Commands coming from the app, going nearly directly to the commands topic. There is a small actor in between, figuring out which asterisk or which topic is this command belonging to, and so it just chooses the commands topic and sending out the command. So we've done that, and we implemented a basic call, or no, an announcement to an echo system, or an echo app, if you would call it. And then we thought, maybe we have a look on performance and timing. We don't know, we want to have an entire rebuild our current setup, but how does it behave? So we tested a bit, and all measurements for the timing part were taken without load. So we had a silent setup in the production system, but it's brand new, so we know what traffic is on there, nothing. And we always took the time, the different components needed from the Stasis start to the answer command, or in zip-wise from the invite to the 200 OK. We always took the median of the test row. I will show them in a short moment. And it was a basic call to an announcement. So there were several things going vice versa. But at the end, the first reaction to the Stasis start was the command answer. So there was nothing in between. So if we have a picture on that, look on that picture again. So from the time the Stasis start event hits our call controller to the time we see the answer command on the network interface, so I did an ngrep, so it's a network interface, it took 9 milliseconds for the akka system to react on that, build up the FSM, know how to send out the command. It was 9 milliseconds, which is pretty fast. Then it comes to the Kafka. There's just 2 times network added on. It took 1 milliseconds from one PC to another, which is okay. Then we have the other side of the Kafka. So on the Kafka machine towards the ARI proxy, we see an add-up of 22 milliseconds. So we have an add-on for each passing through the Kafka of 11 milliseconds, which is not too bad. It's not great, but it's okay for us so far. Then we had an incredible jump just on another network or just another PC. This is caused by firewall, another data center, another kind of network. So we have routing, firewalling, and different data centers. So we learned out of this number, we want to have everything close together and not firewall and no data center jump and so on. Then on the ARI proxy, we see we add up just going twice to the ARI proxy. It adds on 13 milliseconds. So in total for our setup, we take 67 milliseconds to answer a call, which is okay. And then we had a look on the other side, on the Asterisk, on the SIP side, and we see there 202 milliseconds, which is disturbing and a lot. And we figured out, we haven't figured out why yet. But we drilled a little bit deeper, and we saw from the SIP invite till we see the Stasis start on the WebSocket, it takes astoundingly 2 milliseconds. It's incredibly fast. So on the other side, from the command answer, we see on the WebSocket to the 200OK in SIP, it takes 133 milliseconds, which is bad, I would say, or long. Since this is a static time and we haven't seen many shifting between that time, it's okay for now, but we will make some more research in that in order to get that down as well. Would be great if it takes 2 milliseconds as well, then we had a very fast post-die delay. So this was it in terms of timing. Then load capacity, because we are a carrier and we have lots of calls and we want to have load. So we produced load locally on the Asterisk server, which is hardware, using SIP-P. It's a basic call. We have media in them, so we have, we had to press a hash, a pound key once, so we have to had RTP all the time. And basically, we increased the load with SIP-P until the system breaks. So it was fun. It was a basic call to an announcement. There were several things we done in the call. At all, we had 13 events for the call, 7 commands, so 7 replies, and the call duration was about 30 seconds with RTP. So each call was, we answer the call, we playback and welcome playback, we start a recording, wait for the pound key, stop the recording, playback, so the stop of the recording was for free because you can say stop on pound. Playback the recording, playback a goodbye message and hang up the call. And when we get the Stasis end message, we delete the file, so we have no memory leak there. So this was the call we did. The system running on 2 hardware machines serving the Asterisk and the ARI proxy. For Kafka, we use, at the moment, 3 virtual machines. For the call controller, we use 2 virtual machines. And for the backing up for the FSM and for the cache, we use Redis, running on a single virtual machine. Then we started. The first run was mid-load capacity over a long time to see if we break after a certain time. And the second run was increasing load until it breaks. So this is, hope you can read it. What we did overnight, we had 4 calls per second for each asterisk. The test was about 15 hours. We had 213,000 calls for each asterisk, and we had a failure rate from 0.0141%. So, whatever. So it was okay, not too bad. In our Grafana, we see this. I hope you can read that as well. The most upper graph is the channel count, so we were more or less stable with about 120 calls or 110 calls. We were leaking some calls. These were these 30 calls or 0.0141% failure we had, and we just collected those calls so they were added up over time to the overall channel count. Then we had the ARI proxy is written in Java. So we have a virtual machine running, also JVM running, and we had a look on the memory the virtual machine uses. And this was, after about 10 hours, pretty much flat. We haven't seen any increase anymore, so it's stable, kind of. And then we had a look on the call setup delay from the ARI proxy. So we had these 200 milliseconds, about 202 milliseconds, nearly all the time. There were some spikes to the top. We don't know why they happen, but they happen. But it's not too bad. It jumps from 200 milliseconds to 215 milliseconds, so we don't care. This was better than we expected. We expected that we have some memory leaks and fail and so on, but it didn't happen. So then we made the second test run, which was more fun. Pressing always the plus key in CP and look how the system behaves. And we measured out, we have a magical limit of 4.8 calls per second for each asterisk. That doesn't sound much, but it is. In terms of, you have to have this, we have the 13 events and the 7 commands and responses all together, and a very short call time, so it's, I would say enough for us. But at the moment we've seen a problem, we figured out that the call setup delay rises. At the same time, we see in Kafka that the consumer lag rises. So the consumer out of the Kafka was not fast enough. Then we had a look at that, and this is a single process in Java, so we ended up with the limitation of 1 processor. So we could have that made more running in 2 processes or 3 or 4 or 6 processes, whatever. But I think for us, these 4.8 calls per second are enough, since we don't want to have these huge Asterisk instances serving millions of calls a day. Just we want to have smaller Asterisk instances serving not so many calls. So if the Asterisk crashes for any reason, not many calls are infected, just a little bit. So we could have done some optimizations there, but we didn't because it's enough for us. This is what I just said. Then we had a look on what we did if we fit our demands. So this is the same slide from the beginning. This is high available. This is performant, at least performant enough for us. It is scalable. We can just add some other instances and we double or triple the performance. It is possible for the call controller part to have continuous deployment all the time without having run out some calls on a certain machine. So this is continuous deployment ready. We have kind of no untested code just beside these 2 lines in extensions conf. And we guess we have a low barrier for entry. So you can read the Asterisk ARI documentation and understand what we did, hopefully. And since we use akka streams for the most parts, it is resilient. So if any problem occurs during processing of a single message or of a command, whatever, the system breaks on this part, but continues to operate. So yeah, maybe a call is broken, but nothing else. Then we thought about this ARI proxy. There are ARI proxies on the market. But we want to have Kafka as message broker, so there is nothing. But what we could do is we could open source that project. Sounds great, but it's selfish. Our reason to put our ARI proxy open source is to have a clean code. So we are about 40 developers in our company, and if there is a shortcut to do anything, we use it all the time. To make a shortcut in an open source project is kind of impossible, so we have to have clear domains between everything. So we thought it might be a good idea to have this open source. First, to keep ourselves clean, and second, to provide this project to other people if they want to use ARI with Kafka by themselves. We have to be honest, we are not the only ones doing ARI proxies. There are alternatives for that. First of which we have the ARI proxy from Systems, thanks to Sean. This was inspiring us doing what we did. And then we have an ARI proxy from Invisible Ink doing pretty much the same. There's another one from Scrusty, AstaNet ARI proxy. I've never looked deeper in that one. All these three enables you to have code not running on the Asterisk, which is configuring or manipulating calls on the Asterisk. But there are some other options to manipulate calls on ARI when you want to run a local script on the Asterisk. There we have again a Go library from Psychosystem. Thanks again, Sean. We have PHP ARI from Greenfield. Thanks to that. There is a Python and a Node implementation from Digium itself. And there is a Ruby implementation from anybody I never heard about. And it's pretty much dead, I think. There are 2 years, more than 2 years, no commit, but it's working. And if you Google, you find many, many more of them. Yeah, I'm pretty much at the end. Are there any questions? And before you ask, for any good question, I have a book to give away, and I have 4 books, so I want to have 4 questions. I don't want to get them home again.
And he's going to judge the questions to see who gets the 4. Any questions?
In the back, over there.
Okay, we'll start with Lindsay. We'll come back for you in a second.
You know, I already have the book, so you can save it for somebody else. Now, my question was, why did you use Redis and not a compacted Kafka stream to keep the current state that looks like more natural in your case?
So there is this framework we use called Redis, and for the finite state machine, there are different backends you can use to persist your state and your data. Redis is just one of them. There is an already finished implementation. Redis is fast. It's scalable. This is why we used it. Maybe we will change it to MySQL, because we know better MySQL than we know Redis, but who never knows. First, we have to run into a problem before we change it, and so far it's good for us. So it was just, it's there. Therefore, we used it.
Wait.
I mean, as you already have Kafka, if Kafka is down, it's a big deal. But you also depend on Redis, so it's one more piece that may break. That's why I'm asking.
Yeah. There's no persistent implementation or persistent plugin for the finite state machine to use Kafka.
So my extensions.conf file looks very similar to yours. I'm assuming that the ARI proxy is your Stasis app, but is there any way to determine in your extensions file if the ARI proxy is down?
I have a 2-liner in there. The first one is triggering the Stasis up, and the second one is hang up with reason 20. And on the kamailio, we can trigger on the failure code 20, because it's never used anywhere else. I never saw that. We run into the failure root and say, okay, it's reason 20, so it must be the case that there is no ARI proxy connected. So we just take the next asterisk in O and mark it for down for a certain time frame, maybe something like that. Therefore, we did that. We will change that. We will use an AGI in future, or fast AGI in future. So we trigger the fast AGI, then we determine which app we want to use for a certain call, and then triggering the status up directly out of the AGI. So this is a plan for now we have. But at all, the extensions conf will not change that much.
Thanks.
That was a good question. You get a book.
So I have a question, just curiosity. So basically, there was one slide where you were showing, the measurement in milliseconds where things are happening. So how did you, what kind of thing you use to measure those? Because some of them were really down to 2 milliseconds. So did you insert code into the source code to do those measurements?
It was pretty simple. I just switched on an encrypt on a single machine. And then the CPU time gives the milliseconds. So I didn't merge two traces together to get this time, because this 2 milliseconds you cannot synchronize two machines that good. But it's one machine, one trace, and capturing both messages in the same pcap trace, and then having opened that up in Wireshark to see the distance between the both.
Thank you.
I'm sorry about that. Okay.
So my question is, did you consider using serialization mechanism rather than extending JSON like protobuffer to see if it improves the performance?
Yeah, we did. We did that in the first place. The problem is Kafka uses only data types which are serializable. So JSON is serializable, and it's type safe, kind of type safe. We did it in the first place, but then we would have forced all users of that to use Java in the backend. And there are certain people in our company who don't want to write Java code. So if they want to implement the call controller in Node, please do so. All the information you need, you get out of the Kafka. So we don't want to add too much complexity to this JSON object. We just took that original Java, this original JSON object coming out of the WebSocket, put that in another JSON object with some glue code around which asterisk the topic it belongs to, something like that, and then send it through the Kafka. So we want to keep that simple. That was the reason why we use JSON plain. And it's good for debugging. Does this answer your question?
Other questions?
The original one was
You get that?
originally you said you used Asterisk 11 in SIP, and you upgraded to Asterisk 15, 16.
Yeah, not really. We still use Asterisk 11. And then we decided to have an entire rebuild, because the old crap, we don't know, hassle with that. So we doing a full new telco stack using Asterisk 16 now. So it does not, it's not a drop-in replacement to the other one. It's just we are trying to implement one after one feature on the new platform, and then routing the call to the new platform, it belongs to a new feature, something like that. So we will stick to Asterisk 11 for a couple more years, probably. Okay. Unfortunately, kind of.
Security people don't like that.
Yeah, me neither. So I don't like it, but it's a fact, and we have kind of firewall in between, so it's not in the internet directly, so it's secured by kamailio and RTP engine. So it's not that insecure, but it is insecure, and if someone compromises the system anyhow with SIP, hopefully we get that out with kamailio and RTP with RTP engine, something like that, and yeah. That's the true story.
Okay, that's
my last book.
Any more questions?
Great.
Joran, thank you for your talk. Let's thank him, everybody. Remember to go into the app and